Hey everyone, welcome to this explainer. Have you ever stopped to really think about how we actually talk to computers? It's not just typing words into a terminal, it's this massive, fascinating intersection of linguistics, mathematics, and human psychology. Today, we're diving straight into the architectural foundations of programming language design. Which kind of brings up a question, and honestly, I think almost every developer has asked this at some point. Why isn't there just one programming language? Seriously, why do we have hundreds of different ways to tell a machine what to do? Couldn't we have just agreed on one universal language by now and saved ourselves a massive headache? Well, the answer is surprisingly simple, and it's basically the core thesis of our explainer today. It's all about trade-offs. Coding isn't magic, right? It's a series of deliberate, heavily engineered compromises. Every language is a tool. Just like you wouldn't use a sledgehammer to fix a watch, you wouldn't use the exact same programming language to run a tiny embedded sensor as you would to build a massive global social network. Okay, let's dive into this. Here's our architectural blueprint for today. We'll hit 1. The purpose behind the code. 2. Grammar and meaning. 3. Types and memory systems. 4. Flow and abstraction. 5. Translating to the machine. And finally, 6. The ecosystem and beyond. All right, kicking things off with Section 1, the purpose behind the code, designing for a goal. See, before a single rule is even written, designers have to decide on their primary goal. If a language prioritizes raw, bare metal performance, like C, for example, its architecture will fundamentally reject any guardrails that might slow it down. But conversely, if developer productivity is the absolute main goal, like with Python, the language takes on all that heavy lifting so you, the human, don't have to. And if you need ironclad safety without sacrificing speed, well, you have to engineer entirely new concepts, like Rust's ownership model. Or say portability is your main objective, then you'd engineer a virtual machine approach, kind of like Java. Moving right along to Section 2, grammar and meaning, syntax and semantics. This is where we actually frame the house. At a high level, language architects are constantly balancing syntax, which is how the code literally looks, the keywords and formatting, with semantics, which is what the code actually does and means. The tension here is super interesting. You can design a syntax that's beautifully simple to read, but if the underlying semantics, the actual mathematical behaviors under the hood, are overly complex, developers are going to constantly trip over unexpected bugs. And what's really fascinating here is how we map that code to actual logic. It generally breaks down into 3 main approaches. We've got operational semantics, which is all about step-by-step execution. Then there's denotational, which maps the code directly to mathematical models. And finally, axiomatic, which is highly rigorous and focused entirely on proving a program's absolute correctness. All right, Section 3, Types and Memory Systems, the engine room. This engine room is where some of the absolute biggest design trade-offs between performance and safety actually happen. Take the type system, for instance. Do you want safety or do you want speed? Statically typed languages check everything up front at compile time. It can be annoying, sure, but it completely prevents fatal errors before you even run the program. On the flip side, dynamically typed languages give you incredible flexibility and rapid development speed. The catch? You might not find a fatal bug until the code is live in production. Then there's memory management. The eternal bane of developers everywhere. Manual management, like malloc and free in C, gives you godlike control and crazy speed. But one tiny typo and you've created a memory leak that crashes your server at 3 a.m. Automatic garbage collection, like you see in Java or Python, is incredibly easy, but it can randomly pause your program just to take out the digital trash. Or you could use modern ownership-based systems like Rust, which try to give you the safety of garbage collection without that performance hit. Let's jump to Section 4, Flow and Abstraction, Managing Complexity. This is all about how developers keep massive programs from just collapsing under their own weight. We aren't just talking about basic conditionals and loops here, though if, else, and while loops are the starting point. As architectures scale, languages have to introduce advanced flow control, using features like pattern matching, core routines, and async/await mechanisms. And today, concurrency is the ultimate test. Languages literally live or die by how elegantly they can handle running multiple tasks at the exact same time without causing massive data collisions. To handle all that complexity, languages offer different abstraction mechanisms. And these aren't just features. They are entirely different philosophies for how you group code together. Whether it's the strict organized hierarchies of object-oriented design in Java or C++, the pure mathematical approach of functional programming like in Haskell, the raw, step-by-step instructions of procedural languages like C, or even multi-paradigm languages like Python or Scala that let you mix and match to fit your style. On to Section 5, Translating to the Machine, Compilers and Interpreters. Now for the translation phase. Processors, at the end of the day, only speak binary machine code. So how do we get our nice, human-readable logic down to the bare metal? The choice between a compiler and an interpreter is a massive architectural commitment. Do you want the upfront delay but blazing fast execution speed of a compiler? Or do you want the instant startup but heavier runtime of an interpreter? Interestingly enough, many of the most successful modern languages actually cheat. They use a hybrid approach, combining bytecode and virtual machines, to steal the absolute best of both worlds. And bringing us home, Section 6, the ecosystem and beyond, surviving in the wild.
Let's zoom out to the real world for a second. A successful programming language is much, much more than just its core syntax. It's a living, breathing ecosystem. Without a massive standard library, robust third-party tooling, and rock-solid cross-platform support, even the most beautifully designed language out there is going to quickly die in obscurity.
And within that ecosystem, designers have to architect for failure. Let's face it, code breaks constantly. That's just reality. The way a language handles those errors, whether it's throwing loud, disruptive exceptions, silently returning error codes, or strictly enforcing result types, completely shapes your day-to-day developer experience. And as a language lives out there in the wild, it faces the ultimate boss battle: evolution versus backward compatibility. Language designers are caught in this constant tug of war. You have to add modern, cutting-edge features to stay relevant, right? But if you break the millions of lines of legacy code already running in production, your users are absolutely going to riot. Bringing this all together, our source material summarizes it perfectly. Quote, "Every feature, whether it's syntax, typing, memory handling, or performance, affects usability, safety, and efficiency. There is no perfect universal language out there. A beautiful language is simply one whose engineered trade-offs perfectly match the job it was built to do." Which leaves us with a pretty fascinating thought to ponder. We've seen how languages are built for the hardware of today. But as we move into eras of unimaginable AI integration, or even quantum hardware, what will the programming languages of tomorrow need to prioritize? What incredible new trade-offs will language architects have to make next? Thank you so much for exploring these foundations with me today.